Good. All right. Last week of classes. You're doing it. Just hang in there a little bit longer. You can do it. With a little bit of luck, we'll finish new material today. And then there's a last section, which I like to have a bonus question on the final exam that I'll save for Thursday. And then on Thursday, we'll do that, of course, but also kind of a final exam overview, right? Where will the marks come from and what to kind of focus on and that kind of thing. And then that'll be it. Well, besides the final exam part, which is not for a while, right? We're pretty late in the exam schedule. All right. Any questions before we start? All right. So least squares regression. Now, a lot of this, there's a lot. So this is all from last day, and I'll just show you that it's spanning 1.5 pages. But that's only because we're going to build on the values that we found last day, and I don't want to recalculate them. Okay, and so I'm just grabbing them from last day. So these are exactly the same notes as last day. This is from your formula sheet, right? And so we have a least squares regression line, which is a line y hat, right, is equal to b naught plus b1x, where the b1 is the slope, right? So with a slope of b1, and how do you calculate it? Well, we said we're going to use r, which is the correlation, right? And this is all from last week, times the standard deviation of the y's over the standard deviation of your x's. Right? And so, of course, I would need to give you that information, right? R is the correlation, standard deviation of y, standard deviation of x. Once you have the slope, you can use it to find the y-intercept, right? In fact, you need to use it, where you take y bar, the mean of the y's, minus the slope times x bar, making sure you do this multiplication first and then subtract it, right? Which means that you also need y bar and x bar, so I would need to give those to you. So for a regression question, I give you these five things. And often, right, something like this. Usually I'm not as nice and I don't tell you, hey, this is your x bar and this is your sx, right? That's really nice. I'm not that nice. But in a blurb, I would say the mean percentage in poverty was 11.35 with a standard deviation of 3.1. And the mean percentage of high school grads was 86.01 with a standard deviation of 3.73. And the correlation is negative 0.75, right? So it as a sentence. I'd give you a scatter plot usually, right? So you can look at the relationship. You have to describe the relationship. Right? This is a negative, right? Linear, negative, moderately strong relationship from last day. We talked about the 3 things you have to touch on. And then I outlined some potential parts of one question, right? They're all going to build on each other. And so find the slope of the least squares regression line. Well, I give you the information, and so you just plug it in, and we found that the slope was negative 0.62 if we round to 2 decimal places. Find the y-intercept of the least squares regression line. Well, that's b naught, right? Plugging in your negative 0.62, which is the slope, times 86.01. Do that first, which is what I've shown here. then subtract that from 11.35. And again, just rounding to 2 decimal places here, I get a y-intercept of 64.68. Oh. Another part, construct the least squares regression line, right? Or equation, if you prefer. All I want you to do there is take your bare bones y hat is equal to b naught plus b1 times x and plug in the b naught and the b1 or the slope that you found. Right? Now you have your y hat is 64.68 minus 0.62 times x. Okay? And then that's all that question is asking you to do, which usually throws people off, right? They want to do more and it just kind of unravels, but this is all it's asking you for. Okay? Why would I make you do that? Because a follow-up question would be, hey, if you have a state with 80% percentage of high school grads, what's the predicted percentage in poverty, right? So then we use this line to predict values of y. Okay? But before we do that, so this is the end of the review from last day, which is a lot, right? But now we have our line, we have our y-intercept, and we have our slope. New today, I want to introduce, and it's possible you've seen it in other courses, right? But a general interpretation of the slope and a general interpretation of the y-intercept. Yeah. So let's start there. We calculate the slope first, so usually we kind of tackle that one first. So the general interpretation of the slope in this case is negative 0.62, right? But in general, right, it's B1. And so how we interpret the slope is, and this part is very important, for each unit increase in x, we expect a slope increase in the predicted value of y. So I'll write that down. So for each unit increase in x, we expect a slope increase in the predicted value of y. That's the general interpretation, and that applies to any slope. But now, what I want to do, and what I always do, is I make you calculate the slope, right? Find the slope, and then find the intercept, or maybe I'll say interpret the slope. Right? It kind of makes up the order that I do it in. But either way, there's going to be a part. And so I'm going to keep going with these A, B, C, D, E, F, G. There's going to be a lot of parts. And so part D would say interpret the slope. What I want you to do is I want you to take the general interpretation and make it question specific, right? We have an x, we have a y, and we have a slope. So interpret the slope for each unit increase in percentage of high school grads, right? That's our x. So you want to replace this x with something question specific. We expect a negative 0.62, right? That's your slope. Increase will always be true, even though it sounds like bad English, and it kind of is, but it's always true. And so the logic kind of trumps the nice sounding language. Okay, and so increase, or let's say unit increase maybe, in the predicted percentage in poverty. If you feel comfortable taking a negative increase, now a negative increase is a decrease, right? But you want to be really careful that you change it to 0.62 decrease if you're changing it, right? Whereas this sounds wonky, right? But it is true. Okay? And so if it's positive, it's an increase, and if it's negative, it's a negative increase. That implies a decrease, right? And so here, I'll say careful, could write a 0.62 decrease, right? But I want you to think about a negative 0.62 decrease. If you kept that negative on there, a negative decrease is an increase, which is wrong, right? That's not true. So my recommendation is just stick to whatever the slope is, positive or negative, right? And just call it an increase, and that's fine. Right? Because otherwise you have to be really, really careful about the wording. And so when I ask you to interpret the slope, right, then you apply this general interpretation, but make it question specific, right? And honestly, at this point, for part marks, you could just give me the general interpretation. Right? Can't give you full marks, but part marks. Still have to memorize that. Right? You don't really have to memorize it, right? Because you can kind of talk your way through it using this formula, right? Or this equation. Right? But either way, you'll have to interpret the slope. All right. How about the general interpretation of the y-intercept? Let's start there. General interpretation of the y-intercept. I'll add some pages here. Now, what is the y? The y-intercept is your b naught, right? And so your b naught is going to be the predicted value of y when x is 0, right? Force x to be 0, and then you have y hat is equal to b naught. And that is the general interpretation of b naught. And so the predicted value of y when x is 0 is b naught, is the y-intercept. In terms of what you need to replace, right? You're going to replace y with whatever the y is measuring, right? You're going to replace x with whatever it's measuring, and of course you're going to replace the y-intercept with its value. I'm going to highlight what I'm looking for in both of these scenarios, in both of your interpretations. I'll be looking for the unit increase or each unit increase in x for your slope. And then x is 0 is what I'll be looking for in your interpretation of the y-intercept. Part E, then, interpret the y-intercept. Interpret the y-intercept. We want to make it question specific, right? And so the predicted percentage in poverty, or you could say the predicted value of percentage in poverty. Fine, I'll keep the wording exactly as is. The predicted value of percentage in poverty, which is your y value or variable, when the percentage of high school grads is 0, is B naught, which is 64.68%. If you don't put the percent on there, that's fine. Of course, even if you've calculated your slope or your intercept incorrectly, as long as you follow through with your interpretation, that's totally fine, right? Then you won't lose any marks there. Or you won't lose any on your interpretation, of course. Nice. There are more parts, but we have to introduce a couple more concepts before we can get there. So, interpreting the slope, interpreting the intercept, right? That's going to be on the final exam for sure. Any questions? Okay. Oh, too bad. I didn't need that spaces at all. So there's the slides do it way quicker than we did, but we already did it all together. So I'm just kind of skipping them. I put little check marks here, right? Done by hand together. And she's got a slightly snazzier interpretation. I'm good with just using what I told you to use. Well, I think this is on Yeah, here's the one I wanted. So the y-intercept, right, is wherever this line crosses x equals 0, right? And so its lines keep going forever and ever and ever in either direction. And so at some point, it will cross the y-axis, right? Now, this y-intercept really has nothing to do with these values down here. It just is where the line happens to cross the y-axis. We're going to start calling this extrapolation later. Okay? And so what we find is that the intercept is really not of any interest, right? Because it's not very useful, because there are no states with 0% high school grads. Right? And so what we find it is also not reliable. And what we're going to find is that here in this kind of range that we used, and I use range. If you've done math, then you might say, hey, what you mean is the domain. I know. For some reason, I just can't shake it. This spread of data, right, of x values, right, in this distance, I'm going to have fairly reliable estimates, right? Fairly reliable predictions. Whereas anything outside, that's my best guess, is the line, right? If someone told me, hey, there's a state with a 40% high school grads, right? I'd say, oh, okay, that's not what I've been seeing, right? That's very uncommon. My best guess would be this point on this line, right? It's unreliable because I don't know if it behaves the same as it did for the data that I built this line off of, but it is my best guess. Usually when we show the graph, right, we only show the portion of the data that we're working with. And so I want you to kind of notice that here looks to me like if this is 5, let's say this is maybe 75 to 95, roughly. Right? And so you might be tempted to use the graph to find the y-intercept, but it's not going to work, right? Because this is at x equals 75, not x equals 0. Okay. I like my interpretation better, but there's alternate interpretations. They're the same, right? For the intercept, you want to hinge it on, okay, well, it's my predicted value of y when x is 0. And she's missing a key term here. For each unit increase in x, which again is that thing that I said I would kind of be latching onto, y is expected to increase or decrease on average by the slope. I think I like my way. So when we introduced regression, right, lines of best fit, we said, well, one of our goals is to model behavior and to make predictions, right? And so how do we make predictions? Well, if we have our equation, y hat is, what was it, 64.68 minus 0.62 times x. Let me just confirm. Yeah. Y hat is the predicted value of y. Right? And so what we can do is we can plug in a value of x and we can predict the output. So for example, and I wonder, let's pretend that this value here, what does that look like? 82 maybe. Ish. 80, not quite halfway between 80 and 85. So what we would do is if we want to predict the percentage in poverty for a state with 82% high school grads, then you can plug in 82 for your x, and you can get the y hat is 64.68 minus 0.62 times 82. You see. 0.62 times 82 And then 64.68 minus that puts me at 13.84. That would be my predicted percentage in poverty, right? And so what we're doing is this line is the equation that we have. And so I'm plugging in x equals 82, and then my prediction is 13.84, which looks like kind of reasonable on our axis. Now, there's scatter around this line, right? And so there's kind of some uncertainty associated with a predicted value, which we'll get to, right? Because we need to be able to say, okay, well, how predictable is this model, right? And so how reliable is my prediction, right? And that depends on how much spread I have around my line. But first, we need to introduce extrapolation. So extrapolation, I feel like is a term that we use kind of in common language, and we use it to mean kind of outside the realm of things that so it's kind of an extension of what you know, okay? And that is what extrapolation is. And so applying a model, which is this line, model estimate to values outside the realm of the original data is called extrapolation. And so there's a little bit of wiggle room, but kind of between here and here, extrapolation would be outside, interpolation is inside, right? Kind of words. This is interpolation. But for values of x outside, it would be considered extrapolation. And as we've seen, sometimes the intercept is an extrapolation. That's okay. Now, the thing about extrapolation is sometimes we have to extrapolate. We don't have a choice, right? And so what we need to do is we just need to recognize that, okay, here's my best guess, my best predicted value, but then you also say that this, I would consider this unreliable because I am extrapolating. And so here, in interpolation, we have kind of reliable predictions, because that's what we built our line around, and we can see that, okay, things tend to be relatively well modeled by this line in this stretch. But for extrapolation, we have unreliable predictions. The tricky part is it is our best guess, but we do consider it unreliable. What's interesting about extrapolation is now that you know it exists and what it is, right? You'll see it a lot, actually. People love to do it, especially in the news and such. But an example of extrapolation, I think this one is so funny. They have collected information on the men's age at first marriage. Who cares about their second? Right? First marriage, and we've broken it up into kind of 3-year time frames. Okay? Now, this looks to me like it was war times, right? And so, right, kind of heading into things changed after the war. And so then if you're trying to use this line now, if you only focus on the blue dots, that's a beautiful linear relationship. It's a strong negative linear relationship. So for this stretch of X's or years, there's no reason not to use this line. It's a good model, right? The problem is that sometimes we don't anticipate a change like this. Sometimes we do, right? If you think about the heights of children, right? They're constantly growing, but then we have this understanding that, okay, you're not going to use a model built off of kind of 0 to 15 years old to predict the height of someone who's 50 years old, because that's crazy, right? We understand that we stop growing. Most of the time when we're dealing with data, though, we don't have that kind of background knowledge. And so that's why you want to be really, really careful with extrapolation, right? And so here, this line, if we kept using this line, which is an excellent model up until, I don't know, roughly 19, looks like 45-ish, if I had to guess. Then we get this dip, and we have this clearly non-linear relationship here, right? It's still, you could use it, you just would get bad predictions all of a sudden, right? Whereas after 1975, then using this line would give you really, really, really bad predictions, right? Because you should be fitting a different line here, right? And it would look very, very different from the 19 to 1945-ish range. The BBC, culprits as well. Women may outsprint men by 2156. Wow, it's crazy, right? Anyways, they published this article. It's crazy that they let that happen because 2156, that's an extrapolation, right? We're building off of data that we have presumably seen, right? And not in the future. And I guess this is from 2004, so kind of an old example. Hopefully they've taken it down. But the data that they used in the background was this. So if I zoom in here, we've got the years for the Olympics and the winning times. Now, race times are tricky, right? Because you want to be fast, which means your race time is low, right? And so you kind of have to think about it a little bit. But good thing they've got these gender coded, I think. Yeah, men get the blue points and women get the red points. And so we have some observed data for the women, right, in red. And we have some observed race times for the men. Then what they did is they just extended these lines. Now, if you had to kind of guess what these outside lines are, those would be confidence intervals, right? And so, of course, there's some wiggle room, right? We've got our data and there's some variability in our data, right? And so we can build confidence intervals. In this case, I'm pretty sure they're prediction intervals, but they're basically the same. And so what they have is they have uncertainty around this model. Notice that the uncertainty, it's hard to tell, but it keeps getting wider and wider as you move further and further out, right? So as you're extrapolating right? It says, oh, I'm not very sure anymore, right? And then what they did, those analysts, is they said, hey, that's crazy. Here at this point, the women are going to be faster than the men. And then what did they do? They mapped it down to 2156 and they called it a day. That's bad. Don't do that. It's interesting to me that these examples can be found. It's kind of alarming, but all right. Because we have really strong models for the data that we have observed. Right? Notice that we've also got this R squared for each of these. Okay. And so we'll see that in a little bit. So I just want to point out that usually that's part of the output that we get. Okay. And can't remember. Oh, it's on the next slide. Phew. I don't think I could have kept it in much longer anyways. R squared. Now I can talk about it. So R squared is a goodness of fit measure, which as opposed to a chi-squared goodness of fit. And so we use our R squared to communicate basically how reliable our model is. Okay? And the higher, the better. So R squared, the strength of the fit of a linear model is most commonly evaluated using R squared. And so if you're in chemistry, biology, physics, right, you would be comparing R squared values, right? Oh, I got an R squared of this. Oh, wow, that's so great. I know. It'll happen. It'll happen to you. But what's the R squared? The R squared, it's in here somewhere, but I can't find it. R squared is the correlation squared. And for some reason, the typical notation is a capital R squared. Whereas for the correlation, I tend to use a lowercase r squared. But in this scenario, they are the same. Remember the facts about the correlation. Correlation goes between -1 and +1. Right? Now, if I square those values, then I get a value, right? I square a negative, it becomes positive. Then I get a value between 0 and 1, right? Which we usually report as a percentage. So R squared is between 0 and 1, which we usually talk about a percentage. So 0 and 100%. So R squared is the square of the correlation coefficient, which is your R, or capital R, if you prefer. This is the one scenario where I could be convinced to use capital R as opposed to a lowercase r, but I'll still use a lowercase. So the R squared tells us what percent of variability in the response variable, which is your Y, is explained by the model. I'm going to give you a slightly longer definition in a bit. But what that means is that the remainder of the variability, now the variability is kind of the spread around the line, right? So the remainder of the variability is explained by variables that are not in your model, right? Anything that's not X that could be impacting your Y's. And so, of course, there could just be randomness in general, or there could be a variable that you haven't taken into account. And there's a typo here. I think she used the slope instead of the correlation, so I fixed it. So for ours, our correlation was negative 0.75. Once you square it, then you get 0.5625 or 56.25%. A couple of notes. A high R squared tells us that we have a good model fit. We have a good model fit. And in terms of R squared, I like to use R squared. So in general, I should say, in general, R squared is the percentage of variability in Y explained by the least squares regression line on X. Let me add a page here. So what we would say, once we have our R squared, right, I convert it to a percentage if I want to talk about a percentage. And so for us, therefore, 56.25% of the variability in percentage of, or percentage in poverty, right? That's your Y. I'm missing an is explained by the least squares regression line. On percentage of high school grads. In terms of this particular question. That's a long blurb. I know that. Okay. But what I want you to be looking out for is some percentage of variability. Percentage of variability, I want you to think R squared. Okay. As soon as you see that, right, I want you to think R squared. Because R squared is the percentage of variability, blah, 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 blah. I'm not going to ask you to memorize the definition of R squared. I do need you to remember how to interpret the slope and the intercept. It's kind of part of the gig. But I do need you to be able to recognize if I give you the R squared. Right? And so if I tell you 56.25% of the variability in percentage in poverty is explained by the least squares regression line on percentage of high school grads, what would a reasonable follow-up question be to that? You could use that to find the correlation, right? And so linking back to the very beginning with all the information that I need to give you, right, here, I need to give you the correlation. Yeah? But one of the ways that I could give you the correlation is I could start us off and say, well, 60% of the variability in percentage in poverty is explained by the by the least squares regression line on the percentage of high school grads. Find the correlation. Okay? And so that's kind of an alternate way that I could give you the correlation. And so there's kind of two ways that I could give it to you. Okay? Now, remember, this is a negative slope. In fact, maybe I'll snag this here. Copy. Oops, go way down. An alternative way I could give you the correlation is something like this. I don't want to start my parts over. I guess I will. All right. I'll just make up an r squared. All right. 65% of the variability in percentage in poverty is explained by the least squares regression line on the percentage of high school grads. Find the correlation. Right. Now I picked a new r squared just because it's just for practice. Yeah. As soon as you see percentage of variability, right, then I want you to think r squared. Right? And so here, what this tells me is that r squared is 0.65 as a decimal. Now, if r squared is the correlation squared, then if r squared is 0.65, I can solve for r. But you have to be really, really careful because when you take the square root, you get both options, right? You get a positive and a negative option. And so the plus minus root of 0.65 is the correlation. Now here, we need to pick the appropriate sign and that's where, and I'll throw that in here, right? If I have this negative relationship, right, then the only way that my slope becomes negative is through my correlation. And so that means that my correlation has to be negative, right? The correlation is the strength and direction of a linear relationship. And so then, therefore, r would be negative root 0.65, which is a number. Let's read it. So the correlation is roughly negative 0.80622577748 because I can't stop. Then you would have the correlation, right? And then you could use that to find the slope and the intercept, right? So it's just kind of two ways that you could be given that information. Okay. Because it's not in the slides, I'm going to go to your formula sheet. Where is it? Because we've been ignoring this blob, the covariance and the correlation, and we'll keep ignoring it. Don't worry. But I do want to just bring it in so we can see it. It does have a note that capital R and lowercase r are used interchangeably. Now, I've said there are kind of two ways that I could give you the correlation. I guess the third way that I won't make you do on the final exam, but that you should see, just because I can't remember if there's any homework problems that use the covariance, but the covariance is this SXY. And what a mess, right? It's the xi's minus x bars times yi's minus y bars, all summed up divided by n minus 1. Yikes. Or alternatively, but if I told you the covariance is blank, right, then you could use that here, right, to find the correlation that way as well. Because from the question, I have to give you Sx and I have to give you Sy. So the only new component, so the third way, I guess, that I could give you the correlation is if I give you the covariance and ask you to find the correlation. So the third way I could give you the correlation is to first ask you, or to first give you the covariance and then ask you to solve for the correlation. Is to give you the covariance, which is your SXY, and have you solve for R. There's a lot of sums and gross things here. You can just ignore all those. On the final exam, I promise it'll be, I either give it to you straight, that would be really nice, or I give you the R squared and I ask you to find the correlation and then you use that correlation for the rest of your questions. But this is technically an option, but it would be if we had more time. Nice. That was a little segue. All right. Or side step, I guess, more like it. So we've interpreted the R squared, right, because it was this 56.25% of the variability in the percentage in poverty is explained by the least squares regression line on percentage of high school grads. That is your R squared. That's the interpretation of R squared. What does that mean? It means that 44%, right, roughly, right, the kind of the missing chunk of kind of activity in Y is explained by factors other than the percentage of high school grads, which of course makes sense, right? It kind of depends on other things, right? Oh yeah, now I want to go back up to this one here. So these R squareds are quite high, right? I would be happy with an R squared. Just in general, I'd be happy with 60% is still pretty good, right? Even a correlation of negative 0.75, we found had an R squared of 0.56 something, right? And so that correlation is high, but then the R squared gets kind of dampened by that, because squaring decimals, it does weird stuff, right? It kind of makes it smaller. Just confusing, right? But here, what would the correlation be? Right? The correlation R would be the plus minus square root of 0.789. Right? The root of 0.789, so it'd be plus minus 0.88826-ish. That's a really high correlation, right? It only goes to 1. Okay? And of course, when I look at this relationship, I see I have a negative relationship for both of these, which means that my correlation would have to be negative, right? I would choose the negative option. Well, you could do the same thing for the other one, but just to see the relationship between the correlation, which I find is easier to wrap your head around than the R squared. Okay. And get this together. Oh yeah. Any questions about that? Yeah. What I want to talk about next is the region. So the poverty, the percentage in poverty versus a new variable, which we'll call region, which is either east or west. Now this is a categorical variable. Categorical explanatory variable. I just want you to see what that would look like. Now, how it works with a categorical explanatory variable, right? Now I have categories. In this case, I only have 2 categories, right? East and west. Okay. And so what we have is the predicted percentage in poverty is, we're told, is 11.17 plus 0.38 times west. Okay. Now, this is what we call a dummy variable. Okay. Usually we call it a dummy variable. And an indicator variable, but usually we do call it a dummy variable for some reason. And how dummy variables work is it'll be a 1 if it is the west. So it's kind of on, right? Or 0 if it's not the west, which would make it east. Right? And so this is kind of on, off in my mind. Right? So in terms of our explanatory variable, when we have this west can be turned on or it can be turned off, right? Then what happens is the reference level, which is east, right, would be held in just the y-intercept. right? And so here, the reference level, which is your east, is going to be this 11.17, right? Because that's the predicted percentage in poverty when west is off, right? Put in a 0 for west, then you're left with 11.17. And then if you turn west on, right, flick a switch, and you plug in 1, right, then the predicted percentage in poverty for the West is 11.17 plus 0.38 times 1, which would just be plus 0.38. So the intercept is the estimated or predicted average poverty percentage in eastern states, which we found is 11.17%. And that's when we plug in a 0 for the explanatory variable. And then the slope in this case is the estimated average poverty percentage in western states is 0.38% higher than eastern states, right? Because we're using this reference level of the eastern states. So now if I tack on the west and it's adding, right, then the west has a slightly higher percentage in poverty. Nice. So just zeros and ones, dummy variables. What if you have more than 2 categories? Then we have a categorical variable with 4 categories. Typical output would look like this. Now we're going to focus our attention here, because you reach a point where, of course, we're not going to do any calculations by hand. You would use Excel or R or something like that. But what we're going to do is we're going to just focus on the estimate. And so the estimate for the intercept is 9.5. And then with the 4 regions, the Midwest, the West, and the South, let's just call them that for shorthand. Oh, sorry, Midwest, West, and South. So what we can do is you can take this output and you can write out the model. And so the poverty hat is going to be 9.5 plus 0.03 times the Midwest plus 1.79. Now, if they were negative, they would be subtracting, right? But these are all adding. 1.79 times the West and plus 4.16 times the South. So what it would look like is you get 9.5 plus 0.03 times the Midwest plus 1.79 times the West, and then my last one doesn't really have room, plus 4.16 times the South. It can only be one of these regions, right? In fact, if the Midwest is off, the West is off, and the South is off, right, letting all these be 0, then my reference level, right, which region is the reference level, is going to be the region that I haven't listed, right? Which means the Northeast. Everything is in relation to the Northeast. So how you read this is, if you are talking about a Midwest state, right, then you would say the predicted percentage in poverty is 0.03% higher than the northeast, right? Or 9.5 plus 0.03. If it's the Midwest, then it can't be the West and it can't be the South. And so those are turned off and you multiply by 0 and they disappear. So then the Northeast is your reference level. And what if you want to predict the percentage in poverty in the South? Then you would have the poverty hat. You'd still have your reference level, the 9.5. But what you would have is, if it's in the South, then I need to turn the South on, which means the Midwest is off and the West is off, right? And what I mean by that is I'm multiplying by 0, right? So then I get plus 0.03 times 0, plus 1.79 times 0, plus 4.16 times 1. Which would put me at 9.50 plus 4.16, which is what? Oops. 13.66%. So I think predictions with categorical variables is pretty fun. It does involve kind of interpreting some output here, but once you learn how to read this, right, then setting up the model isn't too bad. And then you just kind of flick switches, on, off, whatever you want on. But only one of them is on. So there's a lot of multiplication by 0 that happens typically. Any questions about that one though? It's kind of tricky. I will point out, I'm saving it for next day, but we know what the standard error is. In fact, we know what a point estimate is. Right? We also know what a t is. Nice. And this is going to be a p-value. Right? A p-value associated with some hypothesis test. So that's what I'm saving for Thursday. Usually I have it as a bonus question on the final exam. And I will, I promise. Gotta wait. Which region out of those 4 has the lowest poverty percentage? All of these are adding to my reference level, right? And so because my reference level is the Northeast at 9.5, and then in the Midwest, I would add 0.03 to that, or if it was the West, I would add 1.79, or if it was the South, I would add 4.16. And so that means that the lowest option here is 9.5, which corresponds to the Northeast. Right? It would be different, right? Versus if you had, and maybe I'll erase this first. If I manipulate this a little bit, and if I change this to a negative, which you could get, right? What that would mean is that the West would have a 1.79% lower than the Northeast. Right? And so in this case, it would be the West that would have the lowest. Right? But because all the other ones in the original are adding to the reference level, right, then the reference level is the lowest. Okay. Questions. Just a little discussion on the types of outliers in linear regression. And so outliers are kind of a big problem that we have, right? Especially if we're modeling. So if we have an example like this, right? This lump over here, those are the troublemakers, right? These are my outliers. And the reason they're troublemakers is because, and if you kind of squint, you can see that the line is trying to capture them. Remember how the line is built? It's trying to minimize the distance from all the points to the line, right? And so it's working overtime trying to capture these guys, but most of my data looks like this, right? And so that's probably what I should be modeling. And maybe I should remove these and model these separately because clearly they're from some other phenomenon. The trouble is, as a data analyst, you wouldn't know that, right? You wouldn't necessarily have that background information. And so the trouble is, without those outliers, if you just kind of ignore them, the line might look something like this, right? And it would do a better job modeling the majority of those dots or data points. And so how do outliers influence the least squares line in this plot? Well, right, you want to think about where would the regression line be without the outliers? Right? Looks like it's being kind of pulled up towards those outliers, which is often the case. And so without the outliers, the regression line would be steeper and lie closer to the larger group of observations. There's different types of outliers. This one is way out here, right? Here's my outlier, my troublemaker. And if you now kind of imagine not having that troublemaker, there's really no reason this line would look like this, right? This looks like just a cloud to me. I'm not seeing a pattern, right? And so then you get this kind of false sense of a line or a relationship when there isn't one, right? Because if I was to model just these dots, these data points, I would probably have just a horizontal line, right? Where the slope is 0, meaning no relationship between x and y. And so this outlier, because then the point goes, oh, great, there's something that I could capture, right? And so then that's what's pulling this line up towards this outlier. Whereas if you removed it, which is what you would do if you have outliers, then the first thing you would do is just keep all your outliers in there and fit the model, right? So find your line of best fit. And then what you would do is incrementally, you would remove each outlier and see if there's a drastic change, right? And then it gets kind of murky. If there is a drastic change, do you want to remove those outliers, right? Or maybe they're important, right? Maybe they are valuable information, right, that you don't want to remove. Well, that's a decision for future you, I guess. right? And I don't have a guideline. It depends on if you think these are in here by error, right? Or if they actually should be modeled, right? But what you do is you remove outliers incrementally and see if you get any changes in your regression line, right? Your slope and your y-intercept, and keep removing stuff until there is no significant change, right? So in this case, once you remove it, right, you would get a drastic change in your regression equation, right? And so I would lean towards removing it and making a note in your report instead. Hello? Yeah. Let me mute everyone. I think. So startling. I'll write down what we talked about. If we have outliers, potentially more than one, we usually fit the model with all the data. We usually fit the model with all the data. Then remove extreme outliers incrementally, so just one by one, and refit the model. Then remove outliers one by one and refit the data, or refit the model to see if there are extreme changes in the model. Depends on what field you're in, right? I have biology examples because I've worked with a lot of biologists, but I know they just remove it. Doesn't matter. They just get it out of there. And they refit the model and they say, see there, it should be out of there. And so, but it depends on what field you're in. I think physics might not, because they would be interested in those extreme values. Well, it depends. Outliers are points that lie away from the cloud of points, and outliers that lie horizontally away from the cloud are called high leverage points. So if you think about, well, physics again, I guess, right? If they're kind of far out horizontally, then they have more leverage, just like we saw up here. So this is far out horizontally and vertically, but even if this dot was down here, it would pull this line up towards it. This isn't something I'm going to test you on, so that's why I'm blowing through it. The terminology, no. High leverage points that actually influence the slope of the regression line, right? Like we saw where, okay, if I remove it, then the slope would probably be 0, right? Those we call influential points. And of course, you could visualize it, or you could actually fit it in Excel or some other tool, right? And you could look at the slope and see if it's changed drastically. We're usually okay with the intercept changing, but if the slope changes drastically, then that's something to consider. Physics again. So if we have the log of the surface temperature and the log of the light intensity, so here we've talked about transformations, transforming data to make it linear. Okay, and so then we're able to fit linear models to the log of the temperature and the log of the light intensity, because then it kind of turns it into a linear model. But then we have these guys over here. Those are extreme, and I would say even this one might be a little bit weird. And so what we find is with the outliers, this line is just kind of it's just doing its best, trying to capture these guys and this lump of data here. Whereas without the outliers, then you get this model, right, that does a pretty good job of modeling the data, or most of the data, which is the decision that you'd have to make, right? Do you want to model most of the data, or do you want to model all of the data? And that's something I cannot answer for you, because it depends. And cares. High leverage, I guess. Well, that's because it's out this way. Right. So out. But like I said, it's not something that I'll quiz you on, or final exam you on, I should say. Does this outlier, now where is the outlier? It's this little guy here, right? Does this outlier influence the slope of the regression line? Probably just a smidge, but I'm always keen to keep as many data points as I can. And so in this case, if I imagine my line without this point, I would expect the line to be basically the same, right? And so in this scenario, I would personally keep this outlier in, because it doesn't really change the line that much, and it might provide some valuable information. Ugh. Influential points. None of the above, brute. I don't even want to do this one. We have time, but let's talk about why it's none of the above. Influential points are the ones that are out horizontally and would change the slope. And so influential points always change the intercept of the regression line. I guess not necessarily. Too much thinking. Not necessarily. They could. Influential points always reduce R squared, right? Influential points are when the line isn't fitting as well as it could. And I actually kind of disagree with all these. Skip it. I've got the power. Skip it. So I'm going to. I don't like it. I'll even draw a line through it. How about that? I don't like it. So if we have a cluster of data like this, this is just a cloud, right? There's no reason to fit a model to this, because if I put in a low value of X, right, then I could get any one of these outputs. And if I put in a high value of X, then I would get the same potential outputs, right? And so I would say, just in general, of course, they've drawn the line nicely, right? But here, it could just be a straight line, right? And it's really not contributing anything. In general, this has a correlation of 0.08. which means our R squared is itty bitty, right? 0.0064. It's a terrible model, right? And you wouldn't want to use it for anything. Now the caution here, if you're just looking at numbers blindly and you see a correlation of 0.79 and an R squared of 0.6241, you'd be really pleased with that, right? I said, oh, okay, an R squared of 60% or higher is really good, right? Because then your correlation is quite high, really high. But the only reason, right, that we have these values is because of this outlier that's in there. So you want to be really careful, right, and investigate your outliers. Okay. You guys deserve it. Have a break. I'll just pop into 8.4 on Thursday. But I guess this is the end of official final exam material. Wow. And this will be a bonus on the final exam. So I will talk about it, but on Thursday. If you have any questions, let me know. Otherwise, sort of congratulations on wrapping it up. I'll see you on Thursday.